My name is Zachary Elsberry, and today we're going to be looking at a case study of the Caldecott Tunnel. The reason our group chose this project to look at is because we haven't really talked too much about tunnel construction in this course, and we wanted to explore more about that. Another reason we chose it is because a couple of our group members live pretty close to the Caldecott Tunnel, and we actually use it frequently, and we have been using it growing up, and we wanted to see how exactly it was built and the history of it. So the actual whole process of this tunnel has been going on for over 84 years. The first two bores of this tunnel began construction in 1929 and completed in 1937, with the fourth bore being completed in just 2013, recently a couple of years ago. So the tunnel itself goes through the Berkeley Hills and actually crosses over the Hayward Fault Zone, which is a earthquake zone, so they had to take earthquake effects into account. And so when they first started building the first two bores back in 1929, they used air pressure, which is a technique still used to this day, to help the tunnel from collapsing within itself, and they had to make sure they didn't use too much air pressure for explosions inside the tunnel itself too. They also used shotcrete, which is a type of liquid concrete that they would spray the walls of the tunnels to prevent any leaks and just as a lining for the tunnel itself. The main way they caved out the tunnel was the drill and blast method, which is drilling jumbos, which are portable, which was like a portable carriage, which could be on like the bed of a truck, and it had platforms fitted to hold pneumatic drills, which would create holes, and these holes would then be filled with explosives such as dynamite to help clear out the tunnel through the hills. And that is how the first two bores were mostly completed in 1929 to 19...
Professor, I'm Marissa Freise, and I'll be talking about the present construction of the Caldecott Tunnel. Up until the construction of the fourth award-winning bore, three bores existed, the first carrying eastbound traffic, the third carrying westbound traffic, and the middle bore reversing traffic direction several times a day. Due to this situation, there was an obvious need for a fourth bore to alleviate this congestion. Construction began in 2010, and the tunnel was open for use in November of 2013, costing around $417 million US. This project used a one-team approach, which included Caltrans and the consultants working collaboratively instead of Caltrans reviewing and rejecting designs after consultants finished them. The method used for the construction was sequential excavation, which was also known as the New Australian tunneling method. This was necessary due to the variability of rock formations throughout the Berkeley Hills. This method calls for engineers to examine and assess surrounding rock formations, which will then allow them to determine how far the ground can be excavated before installing the initial lining. The harder the rock, the further they can excavate. Special attention was given to evaluating rock deformation due to the various earthquakes faults surrounding the area. Not only was this bore structurally sound, it also featured state-of-the-art systems to ensure safety to users in the case of an emergency. A fire in the third bore in 1982 that killed 7 people caused an extensive revision to the National Tunnel Fire Safety Standards. 19 jet fans were installed to remove smoke from the tunnel in the incident of a fire. These fans were triggered by fire alarms, carbon monoxide detectors, and nitrous oxide detectors. Caltrans also created the variable message sign system to rapidly suppress any incidents to occur in the tunnel. This system illuminated messages to the vehicles to alert drivers in any event of an accident.
Hello, Professor. My name is Garcia, and I will be talking about the future of tunnel boring as well as summarizing our presentation. So the future of tunnel boring lies within the construction of large tunnel boring machines. As tunnels are built through large urbanized areas, it's important to minimize the above ground disturbances. This is where the large tunnel boring machines come into play. Ranging from 1 meter to 20 meters in diameter, these large machines are able to tunnel through hillsides of any kind of material, either hard rock or sand, at a rate of 10 meters a day. These machines have 4 components: the large cutting head that breaks up the rock surface, the main bearing, the thrust system that powers the machine, as well as trailing support mechanisms such as conveyor belts, which takes out the broken rocks from the tunnel, or even its own power supplies. Each TBM or tunnel boring machine has a different effective environment, and that can depend on anything from the length of the tunnel, the size, the rocks present, or even the amount of groundwater present. To summarize our presentation, the Caldecott Tunnel was very interesting to learn about. It is impressive to see how engineering feat such as this, which was started over 100 years ago, is continued to be used on a daily basis by many people. Even though the practices of tunnel boring has changed from the rudimentary blast and drill, which was very dangerous with the use of explosives, to the more precise and a little bit slower new Austrian method, which analyzed each rock individually. It is impressive that with a few minor restorations and renovations, the tunnel is still safe and able to be used. And this concludes our case study of the Caldecott Tunnel.